Hi, students. This is part 2 of the Chapter 24 lecture on electromagnetic waves. All right, so last time, we discussed Maxwell's equations. We looked at them in a manner in which we're trying to see how everything fits together. What Maxwell wanted to do was develop an electromagnetic theory. Prior to his work, there was no electromagnetic theory. All right, and so Maxwell looked at the three equations of which we the Gauss law of electricity, Faraday's law of induction, and Ampere's law, and he realized there was a missing Maxwell equation. Or for symmetry, there should be a Gauss's law for magnetism too. And so we wrote that law down. And then what Maxwell did is those four equations, which relate electric field, magnetic field, space and time, currents and charge densities. Those four equations plus electromagnetic force law formed the basis of electromagnetic theory. So at that point, we had a full-blown electromagnetic theory. But Maxwell, again, did one better than that. Big change, or big advancement. And that he considered a special problem of a source-free environment where you have no charges and no currents. He rewrote Maxwell's equations in that particular environment. He combined them with the eta vector calculus and derived two wave equations. A one wave equation for the electric field, the other wave equation for the magnetic field. And of course, the solutions to wave equations, a particular special partial differential equation, those solutions are waves that propagate. And as Maxwell predicted and Heinrich Hertz later verified, electromagnetic waves are a complex propagating transverse wave. In one dimension, the electric field amplitude oscillates back and forth, or periodically changes back and forth in one dimension. Perpendicular to the electric field is a magnetic field. So electric field and magnetic field are propagating. They are periodically changing their magnitude in phase with each other, and then this electromagnetic wave travels in a direction that is mutually perpendicular to the electric and magnetic fields. So let's say, for instance, if the electric field is let's say oscillating in the y direction, or I'm sorry, the electric field is oscillating in what I call the z direction, and the magnetic field is going back and forth in the y direction, then they will mutually propagate together in the x direction. All right, so we discussed all of this. And in fact, electromagnetic waves, there's an entire electromagnetic spectrum. Everything ranging from very long wave radio waves through, and of course, radio waves encompass a large variety of waves that we're familiar with. Radio waves include television waves, FM radio, AM radio, and microwaves, and radar. All of those are within the region that we call a electromagnetic spectrum called radio waves. Radio waves are the waves that are created by electrical circuitry or wires. And I explained last time about oscillating charges in an antenna and how that produces electromagnetic waves. So any waves that are produced like this are called radio waves. Now, if you go into shorter wavelengths and higher frequencies, you get to the infrared, and then you go to visible, the very short little short sliver of the spectrum called visible light, which is so important to us as humans. Then we move on to ultraviolet light. And then we get into, again, ultraviolet is the first electromagnetic waves that can penetrate tissue and actually cause damage, cause cancer possibly. And then we continue getting into higher frequency, shorter wavelength, more, and of course with higher frequency comes more power, more penetrating depth. And so we go to X-rays and finally the gamma rays. X-rays are produced by electronic transitions in the atom, usually large ones. And we'll talk about those in due time. We talk about chapter 30 in atomic physics. And then nuclear decay is the only way gamma rays get created. Gamma rays are highly energetic. All right. So, and then we basically walk through the electromagnetic spectrum and discuss how it is pertinent to us. All right. Now, that was it's more of a seminar than anything else, I would say. All right, now we continue, and what we want to talk about now is the energy in electromagnetic waves. So anybody who's ever put anything in a microwave oven to cook it, there should be no surprise that electromagnetic waves have energy. We would like to express the energy of electromagnetic waves in terms of its fields. That's what we're after right now. And so the energy, sometimes it's very obvious to us, like in our cooked food. Sometimes it is not obvious. You don't feel X-rays. You would not feel a gamma ray going through you, but it would do a lot of biological damage. So sometimes it's very obvious about electromagnetic waves, and other times it is not. Now there is energy in electromagnetic waves. So electromagnetic waves, like all waves, carry energy. Right, and so all electromagnetic waves will carry energy. All right, and so so once the wave is created, once the electromagnetic wave is created, the fields carry the energy. I see the fields, electric and magnetic. All right. Yeah, we studied chapters 16 and 17 on waves. It's no surprise that waves carry energy. We discussed that. Now let's see how we can well, first of all, this goes back a little bit into physics 1 as well, but essentially, if you remember, waves, energy for in a wave, and this is a statement that I made back in physics 1. Any wave, the energy is proportional to the amplitude squared. To the square of the amplitude. Okay, this is true for waves on a string. This is true for acoustic waves, sound waves. This is true for water waves. This is true for electromagnetic waves. And nothing different. So we saw that the so essentially this means, so for electromagnetic waves, the energy is proportional to the square of the electric field and magnetic field amplitudes. Okay. All right. And so we're going to now formally derive what these expressions look like. So it's not going to be a formal proof. It's going to be more a college physics style proof, if you will. But so let's start off. Let's remind ourselves about the parallel plate capacitor. You know, the parallel plate capacitor has electric field contained within it, right? To start off and remind ourselves, what did the energy stored in the in the capacitor look like? What form was that? All right, so recall that for a capacitor, the stored energy, or the energy stored in the electric field, can be expressed as was the E sub cap. Just review, we talked about this in the past. E sub cap is 1/2 CV squared. Okay, again, C is the capacitance. In farads, B is the potential across the capacitor. Like say a parallel plate capacitor, potential across the capacitor plates. I'm going to try to be more general though, because capacitors are not all parallel plate. Most of them are actually cylindrical. These are ones I've seen. Okay, now, but let's go, we're familiar with the parallel plate arrangement, right? So let's go back to the parallel plate. So consider, and this is a general formula, all right? Now let's consider the parallel plate arrangement. Consider the parallel plate capacitor. Now we derived the form of the capacitance, right? And that was what? C was epsilon naught, permittivity of free space, A over D, right? Recall that the capacitance, just like the inductance, is entirely dependent on geometry. Again, I do not have to in any way know what the capacitor is made out of. Glare here, it seems. Try to write this over here. All right, C is epsilon naught A over D. All right, there you are. Okay, so again, entirely dependent on geometry. We know another formula for a parallel plate capacitor. Again, for the parallel plate arrangement, we also know V equals ED. So again, the potential is the electric field times the distance, right? V equals ED. So let's combine everything up in this formula here. So if I combine these relationships, what do I get? I have to temporarily erase them. Okay, so for C, we're going to use the parallel plate arrangement. So E cap is, okay, 1/2 epsilon. So C is what? It's epsilon naught A over D. And move this. Maybe the computer's causing that reflection. All right, C is epsilon naught A over D. And then we have V, which is ED. And don't forget, that's squared. All right. And so now let's simplify things. And so we could do so by, we have E cap. Let's kind of maybe write it up here now. Trying to avoid that glare. Okay, so let's just kind of simplify here. So I have E cap, the energy stored in the capacitor. Okay, let's see here. 1/2. I have an epsilon naught. Let's see. I have A. I have a D squared divided by a D that gives me 1D. So I have one, and I have an E squared in this electric field. So let's you know what? Let me use a different variable. Let me use letter E and not confuse electric fields. So the energy stored in the capacitor is going to be U sub cap. Okay, so because we have too many E's floating around. So U cap, U sub cap. So U is oftentimes used as potential energy anyway. So that's not okay. So we have what? We have a square of the electric field amplitude. What else do we have left over? We have the A, the area of the plates, and we have 1D left over. All right. Now, I want to find out. Now, epsilon naught, E, and A are all constants. So I want to figure out what the power is. So how do you figure out the power? Well, the power is the time rate of change of the energy, or potential energy in this case, or work. Well, if epsilon naught, E, and A are constants, what that means is that we have 1/2 epsilon naught E squared A, and we're going to take the time rate of change of D. Again, the electric field is going across the parallel plate arrangement. All right, so this really is D in this particular case is actually a variable, even though it does indeed express the dimensions of the parallel plate in this way. So what this really comes down to is, if I look at the change in the distance with respect to time, that's a velocity. What velocity? The speed of light. Again, the electromagnetic waves are traveling at the speed of light. Again, we're talking about electromagnetic wave, and so we would say that C is this delta D with respect to T. So then what I can actually do is rewrite this as P, the power, is 1/2 epsilon. So let's say 1/2 epsilon naught A E squared, and the velocity C. Yeah, so everything pretty much stays the same except this last one. Okay, now at this point, I'd like to actually talk about the intensity. So remember what the intensity was. The intensity is the power divided by the area. So the intensity, we usually call it I. We've defined this before in our study of waves. It's the power divided by the area. So again, what I've written up here is the power of the electromagnetic wave. Okay. What I'm talking about now is its intensity. So how do I figure out the intensity? Usually I call it I. Well, I'm going to divide it by what? It's going to be the power divided by the area. If I'm going to divide by the area, that means all I'm going to accomplish is canceling out this area right here. It's just going to go away. But I'm dividing by the area. So when I divide by the area, I mean, if it's going to be P over A, then this is going to be 1/2 epsilon naught E squared C, or if I call it, usually it's, yeah, usually they put the C up here. 1/2 C epsilon naught E squared. And that is, and we typically will use E naught because that is the amplitude of electric field. All right. So the intensity of the electromagnetic wave. Where this glare is coming from. All right. Intensity of the electromagnetic wave. Right. And again, E naught is the amplitude. So E naught, remind ourselves, the E naught is the amplitude of the electromagnetic wave. The maximum amplitude, the maximum field that it'll take on. So E naught is the amplitude of the electric field of the electromagnetic wave. Okay. All right. Okay. So those are both, all of these are very important relationships. Okay. Now, earlier on in this chapter, we said there was a relationship between the electric field amplitude and the magnetic field amplitude. All right, so let's keep this. This is actually officially what we refer to as the average intensity. We are bringing up that, I mean, this usually is an average. This would be an average power. We were talking about a periodic wave. This is typically the average intensity. So, pardon me for not writing that down. All right, so let's put this in the parking lot, and I want to use that relationship between the fields, and we're going to derive two other forms of this average intensity. All right, so put this in the parking lot here. Okay, so we know an expression for the average intensity of electromagnetic wave. And again, we said that I average is given as, again, it's the power divided by the area, as intensity always is. And that's given as, in this case, 1/2 C epsilon naught E naught, or E naught squared. to remind ourselves, C is the speed of light. Epsilon is the permittivity of free space. E naught is the electric field amplitude in the electromagnetic wave. And this is the average intensity. So you have a wave, it's a wave, like say from the sun, electromagnetic wave, like say from sunlight, that strikes a particular area, say on the surface of the earth. And the power that is associated with that wave divided by the area is called the intensity. All right. Now, we have one form, but recall earlier in the last earlier in this very chapter, we also stated that we know that we have a relation between the electric field magnitude and the magnetic field magnitude, and their ratio is the speed of light. So we can actually use this to express the average intensity a couple different ways. Let me write this better. Okay, so one way to do it is to literally is to sub out the electric field altogether. So I can essentially write this relation for the electric field, simple cross multiplication. E naught is just CB naught. And I can substitute that directly into the relationship for the electric field magnitude. And what I get is I get I average is 1/2 C epsilon naught, and then I have C B naught squared. Okay, and I can then take, so I can multiply out that square. I average is 1/2 C epsilon naught C squared. No, I mean, I'm not going to combine it with the other C for I'll show you why. B naught squared. Typically, physicists like to express the C squared, this particular C squared, as how we saw it derived earlier when we solved Maxwell's equations and for the source free space, and we saw that the waves propagate at some velocity. And what was that velocity? That velocity we found out was C was 1 divided by the square root of mu naught epsilon naught. So if I multiply the magnetic permeability times the electric's permittivity, these are two constants of the universe. I multiply them together, I take their square root, and I take 1 divided by that, I get the speed of light. So why don't we do the following? Why don't we square this, and that way I get rid of the square root, and we'll substitute it right here. All right, so again, if I get rid of the square root, I just get mu naught epsilon naught, right? What I can do is I can now sub for this C squared. And when I do that, instead of writing C squared, I can just replace it by 1 over mu naught epsilon. And we see quickly that the permittivities cancel out, the permittivity of free space cancels out, and I can write this as I average as C B naught squared is typically how you write it. C B naught squared over 2 mu naught. Typically how you see it written in books. I average C B naught squared over 2 mu naught. In this case, all you see are magnetic properties. In this first expression, all you saw were electric properties. You saw the permittivity of free space and the electric field amplitude. In this particular version, you see the magnetic field and the permeability of free space. That's the magnetic special constant of the universe. So I'm going to put this in a parking lot as well. And that's the second version of this. All right, so again, here's another version of I average, electromagnetic wave. Average intensity, you can write as CB naught squared over 2 mu naught. And there's usually one more way of writing this. And that way is, what we do is, we remember again that there is a relationship that E naught over B naught equals C. And again, what we're going to do now is we're going to this time actually only substitute for one of the E naughts. So again, E naught is CB naught. But we're going to rewrite this equation and write it like this instead. We're going to say, well, I average is 1/2 C epsilon naught E naught. I'm going to keep one of the E naughts, and the other one I'm going to substitute for CB naught. All right. And so this becomes pretty easy. I mean, essentially what we're going to get is just multiply it out. You have the I average will be 1/2 C squared, or actually 1/2 C squared epsilon naught E naught B naught. Okay. And again, we recall that C squared again is 1 over mu naught epsilon naught. And so we can again do is substitute for this C squared. You have I average will be 1/2. We have 1 over mu naught epsilon naught. And then we have epsilon naught E naught B naught. All right, and so we can actually cancel out the epsilon naughts, and finally we can then write that I average. It's the third version. I can rewrite all of this as one more version of it. I average is equal to E naught B naught. What's left in the bottom is 2 mu naught. Okay, so I have 3 forms of the average intensity of electromagnetic field, electromagnetic wave. Again, all of these are equivalent. These are 3 equivalent forms. Of the average intensity. Of electromagnetic wave. Which form do you use? Well, whichever form is most convenient. If you know about electric field and you don't know about the magnetic field, well, you probably would pick the top form. If you know the magnetic field, don't know the electric field, you'd pick the second form. Whatever it is that you happen to know in the problem, this is the one you use. All 3 of these forms are absolutely equivalent. Okay, now one thing to also keep in mind is that, remember, the average is always 1/2 the peak. We saw that for power. Remember the peak power. So remember the peak power was twice the average power. Well, since the intensity is nothing more than the power divided by the area, we can actually also write that the peak intensity is equal to 2 times the average. So we can call this, oftentimes we refer to this as I naught, is your peak. Peak intensity is twice I average. Again, this just comes immediately from the equation that we already know for the power. And we're just literally taking the power and divided by the area, and we're just writing in an equivalent form in the intensity. Okay. This point for the rest of this lecture, I'm just going to work some problems. All right, so I have now covered all the material that I want to cover. Let's work some problems. All right, so OpenStax 24.7. This says, A, calculate the range of wavelengths. For AM radio, given its frequency range, is 540 to 1600 kilohertz. All right, and then B, do the same for the FM frequency range. And that's 88.0 to 108 megahertz. All right, so 24.7 part A says, calculate the range of wavelengths for the AM radio, given its frequency range is 540 to 1600 kilohertz. B, do the same for the FM frequency range, 88.0 to 108 megahertz. All right, this is a pretty straightforward problem. I'm going to erase the board for real estate purposes. But again, we have a range of frequencies. We want to turn those into a range of wavelengths. And so we have a simple equation that does that. And that is the fundamental equation that is true for all waves. And that is that the speed is equal to the wavelength times the frequency. And, for electromagnetic waves, that speed happens to be the speed of light. So we know the frequency. We want to get the wavelength. We can use this equation in order to be able to accomplish that. All right. And so, of course, we can solve for lambda. And we get that lambda is C divided by the frequency. So the frequency is going to go from an F min to an F max. And so you're going to go from lambda min will occur at F max. You maximize the denominator, you'll minimize the fraction. And you minimize the denominator, you maximize the fraction, all right? So we're going to do this exercise for each of the bands. We're on part A right now. Lambda max. Let's do lambda min first. Lambda min, minimum wavelength, will occur where? It'll occur at the maximum frequency. Okay, so again, I'm just going to use 3.0 times 10 to the 8th meters per second for the speed of light. And the maximum frequency for AM radio is 1600 kilohertz. That's 1600 times 10 to the 3 hertz. That means the minimum, again, we're doing AM here. The minimum, lambda min, you work this out, you find out that it's going to be 188 meters. I mean, that is a large wave. That is a wave that is a very long wavelength, 188 meters. You know, you're talking about 3.281 feet in a meter. I mean, that, you know, a little over 3 feet every meter. That's a good size wave. The radio wave, the AM radio wave. All right. So again, it's going to need a very large tower in order to be able to make AM radio waves. You're going to have to oscillate those charges quite a bit. What about lambda max? Well, lambda max, I mean, that's lambda min, 188 meters is big. Lambda max will be C over lambda min, or I'm sorry, over F min. So again, you want to maximize the fraction, you minimize the denominator. And that's going to be 3.0 times 10 to the 8th meters per second divided by, and so what's the minimum frequency? It's 540 kilohertz, or 540 times 10 to the 3rd hertz. And I will find that if I do that calculation, that lambda min is going to equal 556 meters. Again, that is a large, what's going on with this glare? Right over here. Lambda min is 556 meters. Again, that is a very large wavelength. How about FM? FM, I can pretty much do the same thing, except I'm just going to have different numbers now. So FM, if I say lambda min is C over F max, so what's F max for FM radio? Well, that's 108 megahertz. So I'm going to just replace this. And you can't do this, but I have a whiteboard and a pen. So 108 times 10 to the 6 hertz. And so you're going to notice that the numbers are going to start going down. So lambda min now, see, lambda min now is going to be just 2.78 meters, much smaller for FM. And same process, lambda max is C over F min. Well, F min now is the minimum is 88 megahertz. 88.0 times 10 to the 6th hertz. And oops, I messed up last time. That last one was a lambda max. Sorry guys, last calculation I did down here for the 556 meters was actually lambda max. Okay, this was lambda max for AM. Please make a note of that. The other one was lambda min. This is the 188 meters is lambda min. This is lambda max for AM. But for FM, that number gets over to 3.41 meters. So now and the range is, you know, much tighter. So instead of going from like an AM, you're going from a minimum wavelength of 188 meters, which is, you know, in and of itself huge, to 556 meters. That's a wavelength. That's how big the wave is. To quite a bit smaller wave for FM. FM ranges from 2.78 meters to 3.41 meters. Okay, so FM waves are much smaller, much shorter than AM waves. Okay, next problem. I'm going to do OpenStax 24.9. All right, this says find the frequency range of visible light. Given that it encompasses wavelengths, from 380 to 760 nanometers. Okay, well, it's really the same process. If I want to go say F min, and I have wavelengths. Now, before I had frequencies, I needed to go to wavelengths. Here I have wavelengths, I need to go to frequencies. So again, you're going back to what? The equation C equals lambda F. Now you're solving for frequency. Before you're solving for wavelength. So again, the algebra is pretty simple. It's just C over lambda this time. All right. So I'm going to say, well, F min. F min, of course, will happen in unison with lambda max. All right. I'm told what lambda max is. 760 nanometers. I know the speed of light. So again, it's going to be 3.0 times 10 to the 8th meters per second divided by 760 times 10 to the negative 9 meters. F min is going to be quite a bit, much bigger than we saw before, 3.95 times 10 to the 14th hertz. Okay. Minimum frequency at the longest wavelength. So this is red light. Okay, this is red. F max. Well, as you can imagine, it's C over lambda min. All right, that's going to be 3.0 times 10 to the 8th meters per second. All right, and that's going to be divided by the 380 nanometers. 380 times 10 to the negative 9 meters. All right, and we'll find out that F max, when we do that, that becomes 7.89 times 10 to the 14th hertz. Okay, I can block some of this light out here. So again, yeah, so 7.89 times 10 to the 14th hertz. All right, so that's all there is to that problem. OpenStax 24.13. Okay, a radar used to detect the presence of aircraft. Receives a pulse. That has reflected off an object. Uh, 6 times 10 negative 5 seconds. After it was transmitted. What is the distance from the radar station to the reflecting object? What is the distance? From the radar station to the reflecting object. All right, again, open that 24.13. A radar used to detect the presence of aircraft receives a pulse that is reflected off of an object 6 times 10 - 5 seconds after it was transmitted. What is the distance from the radar station to the reflecting object? So first of all, how does radar work? So it's an echo, kind of like, when you, let's say you go behind some vacant buildings and you yell, or you're in an empty room and you yell, and your voice gets sent across the room and it bounces back and it comes back at you, right? That's the echo. Well, radar does that for light. So for instance, if you have a radar station, say there's a radar station here. A pulse gets sent out and reflects off some object. Come out, and it's going to, so it's going to be sent out. We know it's going at the speed of light. It's going to bounce off this object, and it's going to come back. Okay, and then we detect that it's there. We bounce the light off of, we bounce the electromagnetic waves or radar waves, which again is part of the radio, part of the electromagnetic spectrum. We bounce the radar waves off of this object. We can't see with our own eyes, but we can detect it from far away. It comes back, and we see that time. The total time, the round trip time, we were told in this problem, the round trip time was that 6 times 10 - 5 seconds. The wording was, the radar is used to detect the presence of the aircraft receives a pulse that has reflected off an object 6 times 10 - 5 seconds after it was transmitted. 6 times 10 - 5 seconds after it was transmitted means it was transmitted, went all the way down, reflected off the object, came back. This distance, we can use this information to understand how far away the object is. We use symmetry to say, well, the object's at a certain distance d, and half the time was taken to actually get to the object. The other half the time was the trip back, right? And so we know that if we were to say, well, how far away is this? Going back to physics 1, distance is c times t. But what t do we use? Well, we're going to use half the round trip time. So again, we want to find out how far away the object is. Well, we'll have the speed of light, 3.0 times 10 to the 8th meters per second. But we're going to do half of this time. So it's going to be 6 times 10 to the -5 seconds, but half of that. Half the time is what it took to actually get to the object. And if we do that, we find out that d is going to be 9.0 times 10 to the 3 meters. Or 9.0 kilometers. So in just 6 times 10 - 5 seconds, basically 60 microseconds, you can determine that the presence of an object that's 9 kilometers away. And that's just basic tenets of radar. All right, let's look at OpenStax 24.15. Alrighty then. Determine the amount of time it takes for X-rays of frequency 3 times 10 to the 18th hertz to travel A, 1 millimeter, and B, 1 centimeter. All right, so there you go. So determine the amount of time it takes for X-rays, a frequency 3 times 10 to the 18th hertz to travel 1 millimeter and then B, 1 centimeter. Okay, keep that in mind. We know the frequency, we know they're X-rays, and these are the two distances. All right, so I'm gonna erase for real estate purposes, particularly because of this glare. I'm trying to avoid it. All right, so part A, we're gonna look at part A. Now, first of all, it doesn't matter that these are X-rays. All electromagnetic waves travel the speed of light, okay? So again, all electromagnetic waves, I don't care what they are, radio waves to X-rays, gamma rays, whatever. All electromagnetic waves travel at the speed of light, first and foremost. So it's nice that they told us that these are X-rays, but the reality is that's all that tells us is that they're electromagnetic waves of some form. All right. So we know the speed like any other electromagnetic wave. Now we're going to go back to again the very chapter 1, chapter 2 type equation that we just saw, and that is that D equals CT. And we just have a couple different D's. We're trying to figure out what T is. T is simply going to be D over C. All right. And so the first distance we're given is a millimeter, 1.0 times 10 to the negative 3 meters, divided by speed of light, 3.0 times 10 to the 8th meters per second. We find out that T in that particular case is going to be 3.3 times 10 to the negative 12 seconds. Very short duration. That's part A. Well, part B is just like this, except now I'm asking about a centimeter. So instead, it's going to be 1 times 10 to the negative 2 up here, and all I really have to do is multiply by 10. So part B, T is simply going to be 3.3 times 10 to the negative 11 seconds, right? I mean, again, a centimeter is just 10 times the distance of a millimeter. I mean, you could make a statement about that, but there's basically no work to show. Okay, OpenStack's 24.30. That one says, what is the intensity of electromagnetic wave? with a peak electric field strength of 125 volts per meter. All right, so what we're told here, quite simply, is E naught. E naught is electric field strength, 125 volts per meter. Now, I derived 3 equations to discuss the intensity of electromagnetic wave. And so, you know, you're going to want to pick an equation that's based upon what you know. Well, clearly, we don't know anything about magnetic field here. And we can figure it out quite simply by using that relationship between electric field, magnetic field, and the speed of light. But right now, for what we have, the most convenient formula for us would be the one that only contains information about the electric field magnitude. So I would use I average. It's one I would pick. You can do a little extra work, more work if you want to, but 1/2 C epsilon naught E naught squared. That is the average intensity of electromagnetic wave. And of course, all 3 equations are equivalent. I just happen to know about E naught. I don't know anything about B naught. All right. I mean, I can figure it out, but right now, let's do the least amount of work possible. So I average is simply going to be, oh, it's glaring crazy. It's right in the middle of the board. I average is 1/2. I'm just gonna have to fight with it. All right. I average is 1/2 C is 3.0 times 10⁸ meters per second. Epsilon naught is a permittivity of free space. That again, that's 8.85 times 10⁻12 coulombs squared per Newton meters squared. And then E naught squared, I'm given as 125 volts per meter. And don't forget to square that. If I do this entire calculation, I find out that I average becomes 20.7 watts per meter squared. All right, average intensity of the electromagnetic wave. All right. Again, just utilizing one of those equations that I derived. OpenStax 24.32. This says, assume the helium neon lasers commonly used in student physics laboratories have power outputs of 0.250 milliwatts. A, If such a laser beam is projected onto a circular spot, so if such a laser beam is projected onto a circular spot, uh, 1.00 millimeter in diameter, what is the intensity? All right, and then from there, B, find the peak magnetic field strength. And finally, C, find a peak electric field strength. All right, read it again. So we have assume the helium neon lasers, that's the lasers you always see, the ones that shine a red laser light, commonly used in student physics laboratories, have power outputs of 0.250 milliwatts. A, if such a laser beam is projected onto a circular spot, 1.00 millimeter in diameter, what is the intensity? And then find the peak magnetic field strength and find the peak electric field strength. All right, so remember these numbers. So what we're given is a power and a diameter of a circular spot. So we're going to get the intensity the old-fashioned way. And that's just intensity is power divided by area, right? So we know the power. We're told the power is of this laser beam is 0.250 milliwatts. That would be translated to 0.250 times 10 to the negative 3 watts. All right, there you go. The area of the circular spot would be pi d squared over 4, or pi, the diameter is 1 millimeter. Let's translate that, of course, into SI, or base SI units, is 1.00 times 10 to the negative 3 meters. Don't forget to square it. Divide that by 4. We find out the area of the circular spot is going to be 7.85 times 10 to the negative 7 meters squared. All right, so we have the power and the area. It's a simple matter to get the intensity. The intensity is nothing more than power divided by area. So I have 0.250 times 10 to the negative 3 watts divided by 7.85 times 10 to the negative 7 meters squared. I find that the intensity is going to be 318.5 watts per meter squared. All right, so again, I was given the power, I was given a diameter of a circular spot. That's elementary to calculate the area. Power divided by the area is the intensity. All right, so we have the intensity. We'll put that in the parking lot. And now from the intensity, we want to first get the electric field strength and then the magnetic field strength. All right, so again, now you know the intensity. You can pick your favorite of the equations that we have. We have 3 different forms of an intensity equation is expressed in terms of the fields. All right, so I'm going to pick the one. If I want to go to electric field, I'm going to pick the one that has electric field in it, right? So, and nothing more than that. So again, parking lot this, I is 318.5 watts per meter squared. All right, now we know the intensity. Now we want to find the electric field strength that's in that electromagnetic wave. And so we know how to do that. Again, this is an average intensity, so let's make this clear. Intensity you get from this calculation is an average intensity. Okay, for part B, we know that the average intensity, I average, is going to be, well, I'm going to pick, actually, oh, I want to do magnetic field first. Sorry about that. So we're going to do part B, asks for magnetic field first, right? So I'm going to pick the equation that's appropriate for that. So that's CB naught squared over 2 mu naught. All right, and so what do I want to do? Well, I want to solve for B naught, right? So B naught, I multiply the 2 and the mu naught, so I have 2 mu naught, I average, and I need to divide by C. I take the square root of all of that. All right, so again, all I'm doing is doing some algebra. 2 mu naught, I average over C. Well, just go and put the numbers in now. We have 2, magnetic permeability of free space is 4 pi times 10 to the negative 7 Tesla meter per ampere. All right, I average, well, we figured that out in part A. That's 318.5 watts per meter squared. And I want to divide that by the speed of light, which is going to be 3.00 times 10 to the 8th meters per second. And let's take the square root of all of this. All right. And I find that B naught, when I do all this, I keep everything, if I keep everything in SI units, I found that the magnetic field is going to be in Tesla, and that'll be 1.63 times 10 to the negative 6 Teslas. Yeah. 1.63 times 10 negative 6 Teslas is B naught. Right up in the parking lot, right near the glare. B naught is 1.63 times 10 to the negative 6 Teslas. All right, and then the last part, of course, is to get the electric field amplitude. Yes, and of course, I could do it a couple different ways. I can complicate life and just pick one of the other intensity equations, or I can remind myself that there's a nice simple relationship between the electric field, the magnetic field, and the speed of light. So I think, let's minimize the amount of work we need to do and use that relationship. So again, there's more than one ways to solve a problem. I could go straight to the intensity equation for the average intensity in terms of the electric field amplitude, and what I'm going to choose to do is use this simple relationship that E naught over B naught is C. Okay, I know B naught. So when I get E naught is CB naught. Or simply 3.0 times 10 to the 8th meters per second times 1.63 times 10 to the negative 6 Tesla. And I find out that E naught is going to be 490 volts per meter. All right, those are, so it's, interestingly enough, is that you can use a fairly simple calculation to get the I average if you know the power of your laser and the size of the spot, and then you can actually use these neat relationships to figure out the maximum amplitudes of the magnetic field and the electric field that compose your beam, or your laser beam. So again, pretty simple there. All right. Next problem, Opus X 24.33. All right, what does that say? An AM radio transmitter. Broadcast 50.0 kilowatts of power. Uniformly in all directions. All right. A, assuming all radio waves, so assuming that all radio waves that strike the ground are completely absorbed. And that there is no absorption by the atmosphere. Or other objects what is the intensity 30.0 kilometers away? Okay, and there's a parenthetical statement. It says hint. Half the power will be spread over the area of a hemisphere. All right, so again, half is going to the ground, half is going to the atmosphere. So half the power will be spread over the area of the hemisphere. There's a part B. Part B says, what is the maximum electric field strength at this distance? Okay, this says an AM radio transmitter broadcasts 50.0 kilowatts of power uniformly in all directions. A, assuming that all radio waves that strike the ground are completely absorbed and that there is no absorption by the atmosphere or other objects, what is the intensity 30.0 kilometers away? And they give you a hint. Half the power will be spread over the area of a hemisphere. Or we'll use that. And then B, what is the maximum electric field strength at this distance? All right. So, all right. So we're going to erase this for real estate purposes. All right, so let's be clear here. So the lower half, look at part A here. So lower half of this spherical distribution of power. So it's going to be, so again, when you're distributing power, you have a power source, and it's going to distribute it over a sphere. All right, so it's going to distribute over a sphere, and again, there's going to be half of this sphere is going to be the ground. So if this is the ground, this gets absorbed. So it's getting spread uniformly all around the hemisphere. That's what this problem is saying, is that this is the atmosphere, and this is the ground. It's going to, anything down into the ground. I mean, there's going to be electromagnetic waves are going to be shot in all directions, but the ones that get to the ground are going to be absorbed. You're also not going to have a multi-bounce problem, right? And so the lower half of this spherical distribution heads to the ground. Right, where we assume total absorption. And we do not encounter the multi-bounce problem, it's called. Multi-bounce problem is, well, let's say you got some place in space, and you know there's going to be some electromagnetic waves going to come directly to it, but you might have another one that bounces off the ground and comes to it too. That kind of confuses things. There's, you get more energy than you anticipate because of multi-bounce. But we're going to assume that multi-bounce issue does not happen. It's not reflecting off the ground. Okay, that's what the multi-bounce problem is. So we're going to assume that doesn't happen. So the multi-bounce problem of reflected waves interfering with the emitted waves in the upper hemisphere, which heads to the sky. So again, we're going to assume that we do not encounter the multi-bounce problem of reflected waves interfering with emitted waves that head to the sky. All this is really saying is we do not have to worry about multi-bounce. All right. Now, so again, let us imagine a sphere. radius 30 kilometers. Okay, with a transmitter source at the center. Just like I drew a moment ago. Okay. The intensity of electromagnetic radiation. At the distance of 30 kilometers, all right, is given by the power divided by the surface area of the sphere. That's the areas, power over area. Okay, and so intensity is always power divided by area. In this case, it's going to be I average is that power divided by the surface area of a sphere, which is 4 pi r squared. And we're going to say that r is 30 kilometers. We're going to draw a sphere of radius 30 kilometers about the transmitter. So power will be distributed uniformly. It's called isotropically, is the official word, all about its source. And that power, those electromagnetic waves are going to cross a spherical, an imagined spherical shell 30 kilometers away. So what is that? What intensity is that gonna? What intensity is that gonna be? Well, again, this would be an average intensity. Let's put the numbers in. So let me erase this. Okay, so power or average intensity, I average, is the power over 4 pi r squared, or I average is going to be 50 kilowatts, 50.0 times 10 to the third watts, divided by 4 pi 30.0 times 10 to the third meters squared. Now, that original hint, you might think, well, why don't you take the power and divide it in half over the hemisphere? Well, again, it's the same problem as if I took the entire power and divided it over the sphere. Again, it's power is being distributed. It's important here is that we don't have a multi-balance problem. So I could literally just consider all the power going about a sphere with the understanding that half the power is being absorbed anyway. So I mean, I could do the following. I could call this 25 kilowatts, and of course I would go I would do half a half a sphere or a hemisphere. So I divide that by 2. I divide that by 2. Comes out to be the same calculation. So I just kept it like this. So again, I average then becomes 4.42 times 10 to the negative 6 watts per meter squared. All right, so that's the intensity 30 kilometers away of this AM radio station. Now we know the intensity. We want to see, we want to understand what the magnitude of the electric field of that electromagnetic wave is. So let's put this in a parking lot. I average is 4.42 to the negative 6 per day. All right, I average is 4.42 times 10 to the negative 6 watts per meter squared. All right, part B, we want to figure out what the electric field strength is, or the amplitude. All right, I think I wrote that a little too high. Parking lot, I average is again 4.42 times 10 to the negative 6 watts per meter squared. All right, so we would want to pick the most appropriate formula for the average intensity, and of course I'm looking for the electric field. I would say that I would pick that the I average would be 1/2 C epsilon naught E naught squared. And solve for E naught. All right, in so doing, I can say that E naught, okay, I'll multiply by 2 and divide by C epsilon. So I have 2 I average divided by C epsilon naught. Take the square root. Okay, that's going to be 2 times 4.42 times 10 to the negative 6 watts per meter squared, and divided by 3.0 times 10 to the 8th meters per second, divided by epsilon naught, the permittivity of free space, 8.85 times 10 to the negative 12 coulomb squared per Newton meters squared. Square root of all that. Find out that E naught, the magnitude of the electric field, or the amplitude of the electric field, making up the electromagnetic wave, becomes 5.77 times 10 to the negative 2 volts per meter. All right, 5.77 times 10 to the negative 2 volts per meter. That's your electric field amplitude. All right, let's do one more OpenStax problem. OpenStax 24.35. Okay, this one says a 2.50 meter diameter university communications satellite dish. A 2.50 meter diameter university communications satellite dish. Receives TV signals have a maximum electric field strength of and that's for each channel, or for one channel, of 7.50 microvolts per meter. 7.50 microvolts per meter. What is the intensity of this wave? Okay. B, what is the power received by the antenna? And C, if the orbiting satellite broadcasts uniformly over an area of 1.50 times 10 to the 13th meters squared, a large fraction of North America, how much power does it radiate? Okay, again, reading this again, 2.50 meter diameter university communication satellite dish. Okay, some satellite dish, 2.5 meters in diameter, receives TV signals that have a maximum electric field strength for one channel of 7.50 microvolts per meter. That's E naught. A, what is the intensity of this wave? B, what is the power received by the antenna? C, if the orbiting satellite broadcasts uniformly over an area of 1.50 times 10 to the 13th meters squared, a large fraction of North America, how much power does it radiate? Okay, keep these numbers in mind, and these are real estate. Oops, what's X 24.35? Okay, so part A, what do you know? We know the satellite dish is 2.50 meters squared, or 2.50 meters, right? Let's calculate the area of the satellite dish. Area of the satellite dish is pi d squared over 4, or pi times 2.50 meters, quantity squared, over 4, or that'll be 4.91 meters squared. Area of satellite dish. Okay, so electromagnetic waves are coming, have been sent out from that satellite. They're being received by the satellite dish. All I really know is the electric field intensity, or the maximum electric field strength, or electric field magnitude. And I was told that that's 7.50 times 10 to the negative 6 volts per meter, microvolts per meter. So 10 to the negative 6 volts per meter. That's all I know. And I want to find the intensity. Well, I average is going to be 1/2 C epsilon E naught squared. Well, I can calculate straight out of the box. I have 1/2 3.00 times 10 to the 8th meters per second. Epsilon naught is 8.85 times 10 to the negative 12 coulomb squared per meter squared. And I have 7.50 times 10 to the negative 6 volts per meter. Okay. And of course, that electric field is squared. You can see it over there. All right, I average. When I work all that out, I find out the average intensity at my satellite dish, or university satellite dish, will be 7.47 times 10 to the negative 14 watts per meter squared. All right, so again, what did I do? I averaged 1/2 C epsilon E naught squared. 1/2 speed of light is 3.00 times 10 to the 8th meters per second. The permittivity of free space is 8.85 times 10 to the negative 12 coulombs per meter squared. And E naught was 7.50 times 10 to the negative 6 volts per meter, and I had to make sure I squared that. And then I got this average intensity. That's the intensity at the satellite dish at the university. Now, how much power was received? All right, so let's put the intensity calculation in the parking lot. Now we want to find the power received by the communication satellite. All right, so in the parking lot, I have 7.47, and this is I average is 7.47 times 10 to negative 14 watts per meter squared. Okay, I average, looking at a different way, is the received power. We'll call it P sub R. Power received by the satellite dish divided by the area of that satellite dish. Okay, so I know I average, I know A, I want to figure out what P sub R is. Well, just a cross multiplication, right? So P sub R is none other than I average times A. P sub R is the average intensity I just got done calculating in part A. 7.47 times 10 to the negative 14 watts per meter squared, and then multiply by the area of that satellite, which I earlier determined to be 4.91 meters squared. That's one of the first calculation I did in this problem. I find out that the power received by the satellite dish is 3.67 times 10 to the negative 13 watts. Okay, that's a very weak power. So oftentimes, there's satellite dishes are designed to reflect energy at a central location because the power is very weak. All right, that's your received power. Now, we now like to determine the power that was actually transmitted by the satellite itself, okay, from space. Okay, so this is a piece of bar. I don't need that any longer. So from space, what we know is that we're still going to use the fact that we have the average intensity, but now we're going to look at transmitted power. The transmitted power, I'll put P sub T, that's from the satellite in space itself, again, is I average. But this time, it's broadcast over an entire area, a good amount of North America. Area total. So the transmitted power, the power that's actually sent out, distributed over this entire area, is going to be, again, you're picking up a little tiny bit of it. The university satellite, you're picking up, the intensity is everywhere the same where the power is being transmitted. It's the same over the entire swath of North America. You're picking it up as some little part at your university satellite's picking up a little part of it, but the intensity everywhere is the same. All right. And so now, how did you get this? Well, you get this average intensity, but you're distributing it over a very large area. So this tells you your transmitted power. Okay, same intensity, 7.47 times 10 to the negative 14 watts per meter squared. But now you're distributing it over a wide area of 1.50 times 10 to the 13th meters squared. So your transmitted power will be 1.12 watts. And that's the power transmitted from satellite itself. All right. There we are. All right. I have one more topic that's in this book. And it turns out that this topic was actually covered toward the end of chapter 27 of OpenStax. All right. And this topic is called electric polarization. Okay, electric polarization is, as we know, again, we're going to talk about light right now. And so as we know, light, visible light, when we say that, is one type of electromagnetic wave. All right, and so, again, electromagnetic wave is a transverse wave where the electric field vector oscillates in one dimension. The magnetic field oscillates in a perpendicular direction to the electric field. The magnetic field vector and the electromagnetic wave propagates in a direction that is mutually perpendicular to the electric and magnetic fields. All right, so I'm going to bring up a picture here from the book. Give me a moment. I have to bring the book up actually real quick. Okay, 1 second here. All right, so remember, this was, well, anyway, while this is coming up, remind you again, so light is one type of electromagnetic wave. Electromagnetic wave is a transverse wave where the electric field vector oscillates in one dimension. The magnetic field vector oscillates in a direction perpendicular to the electric field. And the electromagnetic waves propagate, or propagates in a direction that's mutually perpendicular to the electric and magnetic fields. All right, and so let's again take a look at what this looks like. I'm going to be heading to chapter 27 of OpenStax. Again, we are still on chapter 24 of our book. OpenStax decided to put electric polarization in the same chapter as wave optics. So I guess it's just a choice they made. Okay. So let's remind ourselves. Be sure my screen. Okay, so what we see is exactly what I'm talking about, in that you see the electric field is going along one plane, magnetic field is along a perpendicular plane, and the propagation direction is a direction that's mutually perpendicular to the electric field and magnetic field. So in this particular picture, electric field vectors are in a sine wave that is confined to up and down. The magnetic field is in a sine wave that is confined to out and in, if you will. And then the electromagnetic wave itself propagates in yet the third mutually perpendicular direction. All right, and so now what you see is one such wave. the direction of polarization is defined as the direction of the electric field vector. All right, so when you talk about the direction of polarization of a wave, it is defined as the direction or the direction in which electric field oscillates. All right, and so all right, so that in our pictures, let me stop sharing for a second. Okay, so and again, when we talk about polarization, this has nothing to do with the polarization. This is not has nothing to do with charge polarization. Okay, so again, do not get this confused. With the polarization of charge. All right, so again, this is a totally different polarization. So we've talked, so sometimes some scientific terms, even in the course of just one subject, can have multiple meanings. We'll see that a few times in this chapter. But polarization, we said in the past, the polarization was all positive charges in one side and all negative charges on the other side. This has nothing to do with that. All right. So what you just saw is, we saw an example of electromagnetic wave with its electric field in one direction, its magnetic field in a direction perpendicular to the electric field, and the electromagnetic wave propagating in a direction that is mutually perpendicular to the electric and magnetic field direction. All right, so by convention, we define the polarization of electromagnetic wave by the direction of its electric field. All right, so we define, and this is the polarization in this context, we define the polarization of an electric field. Let me just write this up here. I have this annoying glare today. we define the polarization of electromagnetic wave as the direction of its electric field. All right, that's what we call by the polarization. That last picture showed you, let me again remind you. So if you look at this wave, the electric field is in this direction. Again, it's up and down in the picture. Well, the direction of polarization is parallel to the direction of the electric field. That is a definition. That is a convention of electromagnetic theory. Okay, the direction of polarization is parallel to the direction of the electric field. All right, as I just showed you. All right. So again, the direction of polarization, called the direction of polarization. Is parallel to the direction of the electric field. Vector. All right, so that is the definitions. But in general, almost most light sources like sunlight consists of randomly oriented consists of electromagnetic waves, many electromagnetic waves, with randomly oriented polarization. All right, so in general, there's many polarizations just in we refer to this as unpolarized light. This is called unpolarized light. So give you another picture. Going back, share my screen. Oops. Now, again, that's just one polarization I'm showing you right there. But go down a little bit further. OpenStax, chapter 27. And we see more of a, hang on one second. More of a typical example. This is just what you're seeing coming at you. For instance, you have light that is in all different polarizations. Again, the electric field, there's a whole bunch of different electromagnetic waves that are combined together in a single beam of light. And all the electric fields, again, the electric polarization is defined as a direction of electric field vector. You see a whole lot of, and this is just a few that are shown here. There's almost like an infinite number of electric field vectors. Like every direction is represented in unpolarized light, even though they all move together again in the same propagation direction. All right. So what we want to do is, one of the things we like to try to do is develop what's called polarized light. All right, and so we make what are called Polaroid materials. So Polaroid materials were invented by the founder of Polaroid. Of Polaroid Corporation. And his name is Edwin Land. Okay. Polaroid materials were invented by the founder. So essentially, these materials, Polaroid materials, consist of long parallel polymers. So if you look at it kind of close up, you look at it, really close. These polymers are like parallel strips. Again, these are polymers. From chemistry, hydrogen, oxygen, and oxygen and carbon. These long straight fibers. What they do is when light randomly polarized light or unpolarized light strikes one of these Polaroid materials, the only light that's allowed to go through is the one where electric field vectors are oriented with these directions. All right. So again, if unpolarized light passes through a Polaroid material, only light with electric field vectors parallel to the direction of the I guess you want to call them of the slits, I guess if you will. We'll say the direction of the Polaroid material. Pass. All the other directions are not allowed to pass. So we take a look at another picture that I have from OpenStax. Go back to the book. All right, so next picture, you have totally unpolarized light like you see above. Now this unpolarized light will approach this Polaroid material. And notice that the only light that gets through has an electric field vector that is polarized. Its direction of polarization is parallel to the direction of the axis, if you will, of the polarized material. So this direction that where light is allowed to pass through, this is called its axis. This is called a Polaroid filter. And after this unpolarized light passes through the Polaroid filter, again, the unpolarized light is moving along the directions, passing through the Polaroid filter and is continuing along the direction of the ray. Well, after that unpolarized light passes through the polarized filter, the only light that's allowed to pass through is that which has electric field vectors parallel to the Polaroid axis. So this creates what's called polarized light. All right. So such light is said to be polarized. All right. This is a polarizing filter. This direction of polarization is called its axis, the axis of the polarized filter. Again, light that comes out, as I showed you in the picture, is the only light that comes out is light that is polarized or parallel to that filter. Okay, so it turns out that if you were to go and stack one filter behind the another filter, you can further diminish not only polarized light even further, but you can also diminish its intensity. All right, and so let's imagine for a moment. Let me show you another picture here. Let's go back and share my screen. So we see that light that passes through, unpolarized light that passes through a polarizer, a polarized filter, comes out as polarized, i.e. the electric field vector of all the light that passes through is parallel to this polarizing filter axis. No other light is allowed to pass. What happens if you have a situation like this, where now you have unpolarized light that goes through one filter? I'm looking at picture A. Well, the only light that goes through is going to be parallel to the axis, and let's imagine it goes through a second filter that happens to be oriented the exact way. The two axes are oriented with each other. Well, then that's not really going to affect the light at all. It's going to pass through. But let's imagine instead I look at picture B. Picture B again is the unpolarized light approaching the first filter, just as before. The polarizing axis is vertical. But now I have another filter that's at an angle. With respect to the other one. Well, the only light that's going to pass through is going to be parallel to this second filter. So already you're talking about light that's already been diminished. And there's the only light that you actually get through the first filter is polarized in the direction of that first filter, but then it's going to get further polarized with the second filter, and that's going to diminish the intensity. It turns out that if you actually rotate the second filter by 90 degrees compared with the first filter, you'll actually extinguish the light altogether. That no light will go through. So in picture C, we're going to find out that if you were to actually have the second filter axis perpendicular to the axis of the first filter, that you would actually completely extinguish the light. Then no light will go through that second filter. Now let's see how this works. And go back to the whiteboard. And so you see that I'm going to try to draw a little picture here to help illustrate this. Okay, so in my attempt to draw, let's imagine that I have at some point in space, I happen to have, let's say I'm traveling along this line here. And at some point in space, I happen to have an electric field that's oriented, it's polarized, let's say in this particular direction. All right, and this is, and then I have further down the line is a polarizing filter. That has an axis that's in this direction. This electric field further up the line, and again, the direction of propagation is this direction. And my art is not my strong point. All right. So let's imagine that this particular this is the polarizing. This is the axis. This is a polarizing filter. And the axis that I'm showing is again the polarizing axis. Yeah. Here. So this is the axis of the filter. Let me draw the axis right here where the electric field is. All right, let's kind of just draw this axis. All right. Now, this is the axis that's going to be allowed, so you have this electric field, and it's essentially, this electric field is rotated by this polarizer is rotated at an axis, at an angle. The axis of this filter is rotated at an angle compared with the actual electric field vectors coming in. All right, so we'll kind of imagine this axis, this electric field Now, let's imagine here that this electric field forms the hypotenuse, and the axis would actually form a component. And so if the electric field is rotated compared with the axis, that rotation angle is this angle right here. This is angle theta. This is the polarizing axis. Which forms a component. And so this is the only component that's going to be allowed to pass the polarizing filter. Okay, just the component that's parallel to this axis, this filter axis. Well, we know that intensity goes as electric field strength squared, right? So the intensity of light is proportional to the square of the electric field strength. Again, I said that, right? I mean, well, let me be more clear. What did I actually say? I said the energy is proportional to electric field strength squared. But I know that the energy per time is the power. Well, that means that the power is also proportional to the electric field strength squared. And what's the intensity? That's the power divided by the area. Well, the intensity then is proportional to the electric field strength squared. All right. I mean, again, all of these are proportional to the magnitude to the amplitude of electric field squared. The energy, the power, and the intensity. So I can write something like this. So if I look at the electric field strength, well, again, what part of it's actually going to go through the filter? It's going to be the cosine of it. So in reality, because of this filter strength, what I actually have is E cosine theta squared because of the polarizing filter. So there's going to be so really the intensity is going to go as a cosine squared. And this gives us what is called the law of Malus. The law of Malus says that the intensity after you pass the filter is going to equal the original intensity times the cosine squared of theta. That's the law of Malus. Cosine squared of theta. So as you can see, I mean, in the first picture that I drew, or in the first picture that I showed, if the second polarizer, if you have a polarizer that is aligned with the electric field vector that's incoming, well, that means that the angle between that polarizer axis and the incoming electric field is going to be 0. So that would be cosine of 0, which is 1 squared, or I apologize. This is I naught. So I will be the original intensity. But as you can see, that as the angle increases between the polarizing axis and the electric field vector, well, cosine does what? Cosine of 0 is 1. Well, cosine gets smaller between 0, which is, cosine of 0 is 1, and as you go through it, the cosine squared is going to get smaller and smaller. And when you get the cosine of 90, that's 0. And so if the polarizer has an axis that is perpendicular to the electric field, the incoming electric field, that means that none of it gets through. If that's a cosine, this is 90 degrees, that means cosine squared of 90 is 0. That means that no light intensity will get through. The light will be extinguished. So again, any angle is going to reduce the intensity. The only way you're going to get the same intensity is if again the polarizer has an axis that's lined up with the polarization electric field to begin with. But at any other angle of the polarizer, you're going to see an extinguishing, a gradual extinguishing of the intensity, to the point when you get to when you see the electric field incoming magnitude coming in and you're crossing it at 90 degrees, you will extinguish the electric field. There will be no light intensity. And this is called the law of Malus. Let me see if there's a problem I can do here. All right, let's look at, this is going to be OpenStax 27.84. All right, so again, this was covered in OpenStax chapter 27. Polarization is covered in chapter 24 of Cutnell and Johnson. So again, we're a little out of whack briefly here. All right, this will be OpenStax 27.84. That one says, what angle is needed? Between the direction of polarized light and the axis of the polarizing filter, to cut its intensity in half. All right, what angle is needed? That's our theta, between the direction of polarized light and the axis of the polarizing filter to cut its intensity in half. All right, so how do we do this? I need some real estate here. We want to cut the intensity in half. We will use the law of Malus. All right, so again, we just learned this a minute ago. We use the law of Malus. All right, that again is I equals I naught cosine squared of theta. And what do we want to do? We want I to be half of I naught. We want to cut the initial intensity. The initial intensity, the amplitude of the intensity is I naught. That's the initial intensity of that's the intensity of the light that's coming into the filter. We want to cut that into half. All right. That means these I naughts cancel. And we're asking the question, we want cosine squared of theta equals 1/2. Take the square root of both sides. That means cosine of theta is 1 over the square root of 2. And we know that angle to be 45 degrees. So if I rotate the filter such that this axis is 45 degrees from the axis from the direction of polarization of the incoming electromagnetic wave or the incoming light, if it's 45 degrees, I will cut the intensity of the light down by half. All right, I'm going to do one more problem before I call it a done deal. I'm going to do OpenStax 27.86. Making sure we don't do other chapter 27 problems accidentally. That's going to do polarizer problems. All right, OpenStax 27.86. That says if you have completely polarized light, of intensity 150 watts per meter squared. What is its intensity? Well, what will its intensity be? After passing through a polarizing filter. With its axis at an 89.0 degree angle, to the light's polarization direction. All right. Okay. So, all right. So, if you have completely polarized light of intensity 150 watts per meter squared, there's your average intensity. There's your intensity. What will its intensity be after passing through a polarizing filter with its axis at 89.0 degrees, or with an axis of 89.0 degree angle to the light's polarization direction? Again, that's your theta. This is your I naught. Okay, so you're going to have it pass through a polarizer that has an axis that's at 89 degrees with respect to the polarization direction of the incoming electric field, or sorry, electromagnetic wave. All right, I naught. Let's write down what we know. I naught is 150 watts per meter squared. That's the intensity, the initial intensity of the light before it strikes the polarizer. Theta is 89.0 degrees. So again, this is intensity of light before polarizer, or polarizing filter. Sometimes they're called polarizers. And theta is the angle of between the axis of the polarizing filter and the direction of propagation of electromagnetic wave. So I use the law of Melou. Again, that's I equals I naught cosine squared of theta. Right, so a very straightforward problem. I is this 150 watts per meter squared. And then that's my I naught, and then that's cosine squared of 89 degrees. It's going to be very small. 90 degrees is 0, right? So if I do that, I find out that I has almost been extinguished. It's down to 4.57 times 10 to the negative 2 watts per meter squared. If I were to actually go to 90 degrees, my answer would be 0. A 90-degree angle would actually completely extinguish the incoming electromagnetic wave, the incoming light. All right, that is all I have for chapter 24.